Our final speaker in this session is Tyler Rohan, and he is currently a doctoral student over in our Department of Geology and Environmental Science. And he's doing some really interesting work here where he's comparing citizen reporting of 311 landslides with some field checks and some geophysical modeling to really try to understand, to improve our landslide inventories and think more about it. So Tyler, please take it away.
All right, thank you, Dan, for the introduction. As he said, my name is Tyler Rohan, and today I'm going to be introducing shortly a project that I've been working on, which is landslide susceptibility analysis based on these 311 reports from these citizens. And before I kind of get into the project, I'm going to briefly explain, why it's important to have landslide susceptibility modeling, why it's important to have an accurate landslide inventory, and how citizen reported data can kind of fill that need that's been lacking as well as in publicly available landslide inventories. So the first question, why estimate landslide susceptibility? Firstly, it's essential for mitigating damage of these landslide events. It's key for safe land use planning so we can plan to build important infrastructure in these less susceptible zones, prioritize these preventative efforts for mitigating damage. It can also be key in really identifying the factors that are governing landslide occurrence in a specific study area, as these vary from study area to study area. And it's especially crucial for here in southwestern PA, as we've had increasing landslide damage to infrastructure in recent years. So now a little on, how are we building these landslide susceptibility models? And the first step for building these landslide susceptibility models is we have to define an area that we're interested in looking at and then create a landslide inventory. And these landslide inventories are places of known past landslides that are geospatially referenced. And with these landslide inventories, the second thing we're needing is the geospatial and environmental factors that we believe are having an influence over the occurrence of these landslides. And with these two important data, we can build a quantitative predictive model of landslide susceptibility by evaluating the relationship between the inventory and these geospatial and environmental factors and creating susceptibilities. And now it's mostly pixel-based. And then fourth, with any risk model, it's really important to both validate and determine the uncertainty in the created landslide susceptibility models. So now a little bit about landslide inventories and why they're so important. So again, landslide inventories are this registrar of spatial distribution of where past landslides have occurred. They're crucial for many things, including learning more about the distribution of landslides in an area, the types of landslides, the patterns, recurrence. They're really key in getting statistics of slope failure, as well as I said, they're crucial in building these landslide susceptibility models. They can teach us about the evolution of landscapes that are dominated by these mass wasting processes. There's many different ways in which they can be created. Aerial photography and mapping, or a combination of two, has been important in the past and where we see the majority of these that come from. However, recently there's been a push towards more satellite and terrestrial remote sensing, as well as digital elevation analysis. However, currently, even though landslides are one of the most common natural hazards, there isn't a great extensive work of inventories so that we can monitor them. And that's because creation of these inventories requires mapping of large land masses and can require extensive, expensive work. So not only are we not having a ton of publicly availables out there for researchers to use, they're also not commonly updated over time. So sometimes we're dealing with much older inventories, such as my example I'm showing over here in Allegheny County, which is the Pomeroy inventory from the 70s and 80s that haven't been updated. So, if circumstances or climate are changing, we're going to be not capturing those changes that are occurring on our factors. So now a little bit about what is the 311 system. And don't feel bad if you've never heard of the 301 system. Before I started this research, I actually had no idea it existed. And what the 311 system is it's this brother to the 911 system, and it's for non-emergency phone number that our citizens can call and alert non-emergency municipal services of a variety of different issues. In Allegheny County, Pittsburgh, landslides are one of these issues. This system is widespread throughout the nation and is actually in place in over 300 different cities in the United States and Canada. So now, what can I do with this 311 system? Why is it going to help me with landslide susceptibility? What am I getting from these citizen science data reports? So the first thing is, with the potential of the 311 inventory, is it's publicly available. If you wanted to go look at 311 reports right now, you could go to the Allegheny County data website and download the spreadsheet right now. It updates in real time. So as the reports come in, the data sheet is updated. And key for making these landslide inventories, it records both the location and the time of when the event is reported. So like I said, where most creation of most inventories is this high cost, high effort experience, you could potentially create a not only nationwide database of landslides from this at low cost and low effort, but also, as we've seen in Pittsburgh, a very extensive landslide database as well. However, it's not all roses. Because of the citizen science aspects of the 311 data, there is a high level of uncertainty. The error in reported locations from these citizens isn't quantified. Sometimes the privacy of the citizen reporting the event is taken into account, where actually a lot of times we'll see these events reported at the street locations where the non-emergency services can find the event from there instead of the actual location of where the event is taking place. So as in spatial uncertainty for landslide inventory without a quantification can make inaccurate estimates. So because of this and the potential of the 311, we came up with three main goals for this project. The first is we wanted to quantify the accuracy of the reported 311 locations, quantify the consistency of this 311 data with other landslide locations or with other landslide inventories, as well as see if we were able to produce a high resolution susceptibility map for Pittsburgh, PA with the use of this data. So for this project, we've been using a combination of three different inventories. The first is the USGS landslide inventory, which actually is an inventory of about 1,000 landslides covering all of southwestern PA, mapped by Pomeroy, the example map I showed before. In the 70s and 80s in Pittsburgh, there's about 100 landslide. I also digitized some landslides that are reported through Allegheny County Emergency Services landslide portal, as well as the inventory I was just talking about, the 311, which is the 311 citizen reported calls, and that ranges from 2015 to 2020. 311 has actually lasted longer than 2015. However, it just became digitized in 2015. So that's as far back as it goes when you pull up the publicly available Excel sheet. So as I said, there's two important things when we're building these landslide susceptibility models. We need both an accurate, extensive inventory, as well as the factors that are going to be influencing our landslide occurrence. For this, we used 11 different factors: slope, elevation, position of hill slope, lithology, distance nearest stream and road, profile, curvature, drainage area, land use, and vegetation cover. Most of these variables were self-created through a DEM of Bare Earth DEM. However, others were acquired through PASDA, Pennsylvania Open Data Access, for some of these categorical variables, such as lithology and land use. So now back onto our first goal, and which was quantifying the accuracy of these 311 reported locations. Like I said, one of the benefits of having this 311 inventory is it is constantly updating. So through this constantly updating process, through a summer, I went and field validated landslides as they were reported through the system. And through May of August 2019, I was able to visit 77 different reported 311 locations. Out of those 77 locations, 55 locations that I went to contained a landslide. 7 were duplicate reports, and the mean distance from these reports was around 104 plus or minus 25 meters. That's about our uncertainty with this inventory. So now on to how we're creating these susceptibility maps. We're using conditional probability through the MATLAB software, which associates our landslide occurrences, so those landslide inventories, between different combinations of our influential factors. Weighted contrast help us get it down to the 5 primary factors used in conditional probability, just due to significance and adding a bunch of these different factors. And then to calculate these conditional probabilities, these influential factors are actually broken down into 5 factor classes that span the range of the values in the study area. And we validated using all of our models using a standard AUC ROC validation method. It's essentially a quantitative model for assessing valuation and comparing predictive models. This ranges from 0 to 1, and what it tells us is the probability where a model predicts a landslide where a true landslide indeed occurred. And our ranges for AUCs were around 0.8 to 0.92. The good or acceptable range is usually from 0.7 to 1. So all of our models did fall in decently validated territory or good validated territory. So now looking at our differences between our inventories, we see between our original and field validated inventories, while we do have the same 5 key influential factors, there is one major difference where we see an extreme bias in the original non-field validated 311 landslides to nearest road, and that reverses to slope when we field validate. So a little bit of difference in these 5 key influential factors, as well as the different landslide susceptibility maps we get for when we produce these conditional probability calculations. As you see on the left, this is the susceptibility map for Pittsburgh that we get when we're dealing with our field validated 311 landslides versus our original, and there are stark differences between the two. So showing that, there is going to be some difference with the uncertainty of this 311 data. With consistency to our other 311 data sets, again, we do see this bias towards the nearest road variable, with the USGS and ACES having a higher influence from higher slopes, and as well as some influence for lithology. And again, similar to with the charts I showed before, the 5 highest being nearest road slope, total curvature, near distance to nearest stream, and aspect for this 311 data set. So now another way to potentially improve the consistency of this 311 data was we incorporated a filtering process where we actually filtered our factor maps by a circular filter from 0 to 240 meters filter size. And just to give you kind of an example of how the filter is affecting our maps, I have over here to the right, which shows from non-filtered all the way up to 200 meters filtered. And at each interval, we're comparing the spatial correlation of each of these maps. So if we turn to the left now, looking at the original field validated, or the original 311 versus the field validated, we saw results where actually this filter was helping increase the spatial correlation between the two inventories, however, only up to a point of about a filter size of 120 to 140 meter filter size. And then as we increase this filter size, we saw a drop in correlation. So we do see improvements by using this filter on the original 311 data. However, it only helps up to a certain point. You can't infinitely expand the filter to get similar results. And now the last goal is, can this data be used to create a high resolution landslide susceptibility map for Pittsburgh? So over to the left is what we've created using the combination of the 311 and the USGS data in creation of a landslide susceptibility map. Its AUC validation was around 0.82, which is fairly good. And what we're seeing in this map is it's a little zoomed out, but you can zoom in on a lot of these areas. It's actually a susceptibility map of 10 meter resolution. So for every 10 meter by 10 meter pixel, we've assigned a given landslide susceptibility value, which is a much higher resolution than landslide maps I've currently seen in publications. For the area over to the right is 2 examples of those. So now to summarize what we've been working on. So through field validation, we've determined that there is some uncertainty with the 311 reported locations, quantified to be about 104 plus or minus 25 meters. The 311 has a bias towards distance of road when we're looking at influential variables, but has similar influences of other landslide data sets. Filtration does improve the consistency between 311 and other inventories. So we suggest that the 311 can be used for high resolution susceptibility model, depending on the project goals. So anytime you would want to use this, you do have to account for its uncertainty. The project's not done. There's still much to be done. In the future, I hope to further expand the inventory of validated 311 locations. Another key point, like I said at the beginning, is that with this 311 inventory, we also have temporal data of when the landslide was reported. So quantifying what this temporal uncertainty is could really help us build things such as hydrological and precipitation models. And we hope to do that by examining precipitation thresholds calculated by 311 data in other areas. And also to improve the amount of factors we can use in our susceptibility model creation, we hope to switch out conditional probability with the application of random forest machine learning to decrease that statistical significance so we can add in more variables. So now I'll take any questions. Thank you. And there's my contact email.
Thank you very much, Tyler. There's already one question. The question again is from Henry Mongrain, says, what exactly is aspect as it is a factor in landslide occurrence locations?
Sorry, what was the second one you said?
What is aspect as it is a factor in landslide occurrence locations?
Okay, yeah, so when aspect, we're looking at the orientation of the hill slope. So what aspect is in 0 to 360 degrees. So it's where the hill slope is tilting, and reasons why this can affect landsliding is especially when we're thinking of hydrological properties of the hill slope, and as well as insulation. It can lead to drying and wetting during different times during the day, which can affect the hydrological properties of the soil, which can make landslides more and less susceptible.
All right, are there other questions? I don't see any in the chat right now. Someone wants to shout out, I'm happy to take that too.
Hey, Dan, this is Eric Zorn. I wanted to, if we have time, get back to a question from Tony from my talk, or any other questions that were in the chat that we didn't get to. Do we have time for that, or we gotta get out of here?
I think we have time for it. Let me make one last call for Tyler before we do that, if you don't mind. All right, so there is one question for Eric from Tony. I skipped it just because the other rooms are speeding up and slowing down. I don't know what the heck's going on, but Tony asked Eric, is there a way to determine the size of the sliding wedges? Obviously, more concern would be focused on the larger sliding wedges.
Right, so Tony, you can determine the sliding wedges, like I sort of hinted at, it is a little more complicated because you got to make sure they're spatially related to each other, the fracture sets that are intersecting. But yeah, I mean, if you zone your slope into smaller zones and then rank those zones by the number of possible intersecting wedges, then you can zoom in and find those wedges, one by one, find the wedges that are going to intersect, and then determine the size of that wedge. So yeah, it can be done. It might be a little tedious, but the field work to do the same thing might be a little tedious as well. So you're really you're doing mapping, but you're just doing it on a virtual outcrop. So, and another important thing that I wanted to address before we leave the room, I'm sorry, there, Brian Heinzel at Gannett pointed out in the chat that those large loose blocks that were shown in my presentation were in fact scaled off the slope face because they did pose a risk. So those are no longer there. I just wanted to point that out. So thanks, Brian, for reminding me of that. But that's all I have.